Okay, we'll get started here. Talking about what perturbs equilibrium. How about if I add an inert gas? If I add an inert gas to an equilibrium, will that perturb it by Le Chatelier's principle? So what does an inert gas mean? It doesn't react, and so it doesn't participate in the equilibrium at all. And so if I add an inert gas, will that perturb the equilibrium? No, it will not perturb the equilibrium. What if I add water? You know, water, let's say I have an equilibrium with aqueous solutions. If I have an equilibrium with aqueous solutions and I add pure liquid water, will that perturb the equilibrium? Well, that was tricky because what will water do to the concentration of the aqueous solutions? Yeah, it's going to decrease it because of solution dilution. And so that's a very tricky one because here's where you add a pure liquid and it's going to impact it because it's not because of the liquid, it's because of what it does to all the other concentration. Whereas if I add an inert gas, you know, as long as the volume doesn't change, the concentrations and the pressures won't, the partial pressures. And so there's a mistake that someone caught on the test, on the practice test. The mistake is nitrogen is considered a pseudo-Nobel gas or pseudo-inert gas. That's because it's so unreactive.
What's an inert gas?
Inert gas doesn't react. The Nobel gases, krypton, neon, those used to be called the inert gases a long, long time ago. And then they decided to switch the name to Nobel gases. The reason they decided to switch the name is they found that they can actually get some of the inert gases to react. If some of the inert gases actually do react, then not inert anymore. And so, but not all of them, just xenon. Xenon they could get to react. You know, xenon because it's pretty big. But something like helium, no, they couldn't get that to react. In fact, helium's the most unreactive of the bunch. That is, it's the least reactive. Why? It's got a filled valence shell. Is that it? Filled valence shell. Then why is helium? All of them have filled valence shells. Helium, neon, argon, krypton, xenon. All of them can be considered core electron configurations because they're all filled shells. So. In that way,
Small size.
it's small size. The small size is going to have an extremely high ionization energy, and so in fact it has what element on the periodic table has the highest ionization energy? Fluorine. It turns out it's not fluorine. It's not hydrogen. It's helium. Helium has the highest ionization energy. It isn't reactive though. Because it doesn't want another electron. And so nitrogen is called a pseudo-inert gas because of nitrogen is fairly unreactive. Do you know why nitrogen is so unreactive? Nitrogen is so unreactive because if you go back to the covalent bond energies, you know, the weakest bond on that chart in Chem 1A was like 67 kilojoules per mole. It was an iodine-iodine bond, easy to break. The highest, or the strongest bond on the chart turned out to be a nitrogen-nitrogen triple bond, around 1,000 kilojoules per mole. And so it's a very hard bond to break. You know, in certain biological systems, they can break it, you know, using enzymes. But you know, in a lot of chemical reactions, it just doesn't happen because you need an extremely violent collision to break that bond. It's a really hard bond to break. And so if we add an inert gas like nitrogen, because nitrogen does not participate in that, this is what, somebody have that? The question number on the practice test?
2 NO.
Yeah. What question number was that?
5.
5? Okay. For number 5 on the practice test, then A, B, and then C, no change. And so if you're sure, you know, you don't see the answer, the correct answer on the test, you could write it in. You know, I grade these by hand. But just write it in, no change. In case there was something like that. And so you're positive, you know, or you can come talk to me about it too. But number 5, the correct answer wasn't there. I mean, you're adding an inert gas, it shouldn't have any impact. Nitrogen's not going to participate in that equilibrium, right?
Are there any other gases that are like pseudo inert gases?
Not really, just nitrogen. There are other gases we call inert in particular equilibria. You know, when you're looking at an equilibrium of this and you add some oxygen, but oxygen doesn't participate at all, we'd call oxygen inert for this. But in general, we wouldn't call it inert, whereas nitrogen is so reactive, it reacts with so few things, we tend to call it pseudo-inert, you know, pseudo-noble gas. All right, any other questions from the practice test? All right, so the test is tomorrow, chapter 15. I want to continue with chapter 16 today, so if something else comes up, or if you have any other questions from chapter 15, let me know. We looked at the example 1.0 times 10 to the minus, what was it, 8 molar ammonia last time? Were we working on that particular problem?
Yeah.
Okay. And we did step 1 and step 2. And we saw that step 2 adds, did it add a significant amount of hydroxide to the solution? Step 2? Yeah. In step 2, significant additional hydroxide was, let's see, produced. But this particular problem means that step 1, remember we did the double check for step 1. This means that step 1 will no longer be at equilibrium. Because we recalculated, remember we figured out the equilibrium concentrations for step 1 and double checked that by plugging it into K. And we saw that, okay, it checks out. And then we moved on. And so we went on to step 2. And step 2, did we finish it, right? We got next. We could double check it. It double checks okay. But step 2 screws up step 1, basically. And so what should we do? Well, what we should do is we should fix step 1. You know, now we got additional hydroxide from step 2. We fix step 1. But if we fix step 1, you know what that's going to do to step 2?
Mess it up.
Mess it up. And so what we have here is this problem of endless loop. We cannot solve this problem. Because each time we fix one step, it screws up the other step. So we're in this endless loop. So what should we do? What we need to do is we need to come up with some other technique to solve this. And so these are the techniques for multiple equilibria that we're going to use. What is stepwise? Stepwise is what we've been doing. You know, step 1 and step 2. It works. For example, it worked when it was. Did it work? It worked when it was 0.100 molar ammonia. Did that work? Why did it work when the concentration was 0.100 of molar ammonia? Did we do that problem?
Yeah.
Yes.
Yeah. Why did it work when the concentration was 0.100 molar ammonia?
Because the amount of hydroxide was so small that it didn't affect it.
Yeah, because the quantity of hydroxide that we produced in step 2 was negligible. And so really, you know, if we were to recalculate the K value with the new total hydroxide, it doesn't change anything. And so little hydroxide was produced. But what happened with the 1.0 times 10 to the minus 8 molar hydroxide? Remember that? Okay, stepwise works if successive steps add negligible quantities to previous steps, i.e. 0.100 molar hydroxide, or not hydroxide, 0.100 molar ammonia. It worked there. I mean, go back and look at the numbers. Negligible. Insignificant. Or works if previous step has a very large K. What does very large mean? There's no number, it's just very large. It means that we have 100% reaction. If we have 100% reaction, then no matter what I do to try to push the reaction backwards, I can add a lot more product. But if I add a lot more product, it doesn't push the reaction backwards because K is very large. It only goes one way. And so it's only a one-way reaction. I.e., well, a one-way reaction. You know, that's the way we think about it. You know, all reactions are two-way reactions, but an example of this would be 1.0 times 10 to the minus 8 molar sodium hydroxide. Did we do that one?
Yes.
Yeah. Take a look at that. Did we generate a lot more hydroxide in step 2? Yes, we generated a lot more hydroxide in step 2. Did it screw up step 1? Yes, it screwed up step 1 because step 1 we had a lot less hydroxide. But does it really screw it up? No, because I know that K is very large and it can only flow one direction. Does that make sense? And so stepwise works. But here, stepwise fails. Stepwise fails because here I generate a significant amount of hydroxide, which is going to screw up the equilibrium I just established in step 1. So when stepwise fails, then we have to look for a different method. And so the different method is the general method that we can use for all. It's called simultaneous. I call it simultaneous. There's one more method, which is called combine. And so this is like having the three definitions of what an acid and base is. What are the three definitions of an acid base? Arrhenius, Bronsted, and Lewis. We only need one definition, right? The definition. What is the definition of an acid base? One that encompasses all acids and bases encountered.
Proton donor and proton acceptor?
No, that misses some. For example, that doesn't talk about ligand and metal ion interaction. There's no protons involved there. What is the most general definition? One that encompasses every single acid and base. Not Arrhenius. Lewis. We only need one method. The one method we need to solve all these problems is simultaneous. Why don't we just use simultaneous to solve everything?
Some of the other ways are quicker.
Yes. Quicker and
Easier.
easier. A heck of a lot easier. And so this is why in stepwise we try to do all of them stepwise because it's the easiest. Otherwise we have to fall back on simultaneous. Combined is another simplification. You know, under certain circumstances combined will work, but it's very rare. Well, it's more rare that this method can be applied because those circumstances don't exist in all types of problems. We'll see this in chapter 18 because this is a more advanced method, but it makes your life a heck of a lot easier nonetheless. So now we have to do simultaneous. We can't do the simplification. And so normally what we do is we start off with the general method and then simplify it. In this case, we started off with the simplified method, and now we're going to the general method. The general method, the reason I've avoided it is because it's a lot more work. So let's try it. So simultaneous is just what it says. We have to solve step 1 and step 2 simultaneously. We can't do it one and then the other. We have to do both at the same time. Now, in order to do both at the same time, we have this equilibrium here with the ammonia plus water. This is going to give me ammonium plus hydroxide. This is the KB. B stands for base hydrolysis. Hydrolysis is just water, so it's base plus water. The Kb value we can find in our book. It's 1.8 times 10 to the minus 5. And usually this is the same, Ka value for acetic acid. Ka value for HAC, aka acetic acid, is 1.8 times 10 to the minus 5. And so they're the same to 2 sig figs, but there's no connection there. Some people think there's a connection. There isn't, because the 3 sig figs is different. They just happen around the same number. All right, so we have this, and so we got an ICE table for this, but we also have this. H2O liquid plus H2O liquid gives us hydronium and hydroxide. This is Kw. And so we have to solve Kb and Kw simultaneously. Kw, we know this memorized value, 1.0 minus 8. At what temperature? If the temperature is not specified, do you know what the temperature is? 25 degrees C. And so we have an ice table. H2O liquid, these are pure liquids, so are we going to do anything here? No. Here, if I add, if I'm just looking at the second equilibrium, if I add pure water here, that's not going to change anything. But if I'm looking at both equilibria, if I add pure water, then it screws this one up. So it dilutes everything, changes the concentration. So we ignore it anyway down here. Okay, now how do I solve these simultaneously? Well, I started off with, what was the concentration that we started with here with ammonium? 1.0 times 10 to the negative 8 molar. And the problem is the hydroxide. You know, I get this hydroxide screws up the previous hydroxide, which screws up all the equilibrium, because it's no longer going to be at equilibrium according to Kp. And so what I have to do in simultaneous is I have to solve these so that the hydroxide ion concentration at equilibrium, that is the total hydroxide ion concentration at equilibrium, is the same in both. And so this hydroxide I end up with here has to be exactly the same concentration as this one that I end up here. Otherwise, you know, we get the endless loop issue. And so how do I get this? Well, how I get this is the total hydroxide is going to be the hydroxide that comes from the ammonia plus the hydroxide that comes from the water. And so there are different ways of setting this up. One way of setting this up is like this. I'm going to assume nothing's happened here, right? But instead of putting 0 here like I normally would, do you know what I'm going to put here? I'm going to put Y molar. Now where does Y come from? Y must be coming from the hydroxide from water. And then I'm going to let this react. So I'm going to get minus X plus X plus X. And the X is the molarity of hydroxide coming from ammonia. And so that the total equilibrium hydroxide is going to be Y plus X. The hydroxide from Kw, which is Y, and the hydroxide from Kb, which is X. And so I'll have over here, I'm going to have 1.0 times 10 to the minus 8 minus X molar, and then X molar. All right, the same thing here. For Kw, I'm going to assume nothing's happened here. And so this is 0 molar for the hydronium. Except I'm not going to start with 0 and 0. I'm going to start with 0 and... I'm going to start with 0 and X. Yx, X is the hydroxide that came from the ammonia, from Kb. And then the hydroxide that's going to come from Kw is here, plus Y plus Y. And so at equilibrium, we're going to get Y molar hydronium from Kw, and then the hydroxide is just equal to X plus Y. And so you see that the total hydroxide here is going to be a contribution of both equilibria simultaneously. And so this is it. And rather than solving for an X, now we have to solve for an X and a Y. And so if we have two unknowns, we need at least two equations. Can we come up with two equations? Yes. You know, the Kb equation and the Kw. And then wrap them together, figure out what X is or what Y is, and substitute, solve for the other. Now, when we have two equations and two unknowns, it seems like an easy thing to do, right? Just solve for X or Y. But it turns out that it's not as easy as it looks. So try this. Solve for X and Y. See if you run into problems or see if it's pretty straightforward. You can try it here. Plus, in the homework, I give you two of these. You know, two of these where you're going to have to solve simultaneously. Unfortunately, the solutions manual made a mistake there. And so the two that you're going to have to solve simultaneously in the book is one is like HCN. I forgot, it's like 1 times 10 to the minus 7 molar HCN. The other is ammonia. I think it was like 1 times 10 to the minus 9 molar ammonia, something like that. It's HCN and ammonia. Look at what mistake the solutions manual made. You'll see it, it's pretty obvious. All right, so that's simultaneous. Normally what I do with these, you know, because there's a lot of algebra involved here, and the algebra solving for X and Y takes time, more so than, let's say, successive approximations. So sometimes what I do on these tests is I write a bonus problem on the board. You know, usually I write some information on the board that you might need for the test, like K values and that kind of stuff. Sometimes I'll give you a bonus problem you can solve for if you have time. For extra points. Also, you know, if you have questions from the homework, you know, I can answer those as well in class. But I'll let you finish this, and then you can compare. You know, your answers. And then when you do the double check should both check out okay for both equilibrium. Okay, are we good with that? All right, let's go on to more than two equilibria. And that's what we have here with polyprotic acid. Polyprotic acids would be like phosphoric acid. Phosphoric acid would be what we call a triprotic acid because it has 3 acidic hydrogens, H3PO4. And polybasic bases. A polybasic base, would that have more than one hydroxide? Yeah. For example, calcium hydroxide would be a dibasic base because it has 2 hydroxides, right? But polybasic bases don't have to have more than one hydroxide because when we're thinking about these, we're just thinking about, in terms of Bronsted, being able to accept more than one proton. And so a polybasic base would be something like phosphate. You know, phosphate is what we call a tribasic base. Why is it tribasic? It's tribasic not because it has 3 hydroxides. It's tribasic because it can accept 3 hydrogens, you know, to form H3PO4. And so how do we handle these? You know, when we have polyprotic acids and polybasic bases, what do we do with those? And so let's start off with an example. This example would be sodium phosphate. Let's say I had a 0.100 molar sodium phosphate solution. A 0.100 molar sodium phosphate. Is sodium phosphate a strong base? Weak base? Or what? Weak base. Weak bases do what? They partially hydrolyze, partially ionize. And so does that mean just some of the sodiums break off, but not all the sodiums break off because it's a weak base? Is that what it means? Like, you know, just some of the sodiums will break off because sodium phosphate should be a weak base, right? Not all the sodium should break off. Weak bases are weak electrolytes. Weak electrolytes partially ionize or partially hydrolyze in water. So true or false, just some of the sodiums break off, not all. We get partial dissociation.
Going with false.
False?
Okay.
We get complete dissociation?
No. I think it stays intact.
Stays intact?
Yeah.
Most of it stays intact? Okay. Well, this is a kind of a trick question because when I think of sodium phosphate, I don't think of sodium phosphate as being a base. I think of sodium phosphate as being a soluble salt. Sodium salts are soluble. Soluble salts are strong electrolytes. You know, the strong electrolytes comprise 3 things: soluble salts, strong acids and strong bases. Those three things are strong electrolytes. And so when I think about sodium phosphate, I'll call it step I. Sodium phosphate is a soluble salt. Therefore, soluble salts will completely dissociate to sodium ions and phosphate ions. Soluble salt is what we call a strong electrolyte. And we have a K value associated with this. K value is very large. Whenever we have a strong species, whenever we have a strong electrolyte, which is a soluble salt, a strong acid, or a strong base, we expect K to be very large. And so that means if we start off with 0.100 molar here initially, and 0 molar here, and 0 molar here, we can assume that this is going to go one way. And we're going to end up with 0 molar sodium phosphate molecules intact. How much sodium? 0.300 molar sodium ions and 0.100 molar phosphate. And so this is weird because of how I differentiate. For example, sodium hydroxide. Sodium hydroxide, the first thing that comes to my mind with sodium hydroxide is not strong base. Do you know what the first thing that comes to my mind? Soluble salt. So sodium hydroxide is a soluble salt, therefore it's going to ionize 100% into sodium ions and hydroxide ions. Then once I have hydroxide, then I think strong base. And so hydroxide should have a very large Kb. Right? Well, the same thing. So, once we have phosphate, now I have my tribasic base. And so here in step 1, let me go right over here. Now I'm going to go to step 1. Step 1 is phosphate can accept a proton. Now, will it accept 3 protons simultaneously at the same time? Well, in fact, where is it going to get protons from? This is just sodium phosphate dissolved in water. So I just have base in water. Where are the protons coming from? What's the strongest acid? I know what the strongest base present is. The strongest base is phosphate. What's the strongest acid present? Water. The only place the protons are going to come from are water molecules. And does phosphate attack 3 water molecules simultaneously, picking up 3 protons and going to H3PO4? What do you think? It has this 3-way collision. That is, there's phosphate in the center and 3 water molecules collide with it same time, picking up 3 protons? Or do you think just 1 water molecule collides at a time? 3. It turns out just 1 water molecule collides because of how it's oriented. And so this happens in steps. It doesn't happen all at once. And so it picks up 1 proton from water to form monohydrogen phosphate and what's left over? Hydroxide. This is called Kb, base hydrolysis for the base phosphate. It's also called Kb1 for phosphate. But the problem is Kb1 or Kb for phosphate isn't given in the book. I don't see it in the book, and I don't see it on this chart up here. Kb for ammonia is given in the book, 1.8 times 10 to the minus 5. But when I look at this chart over here, there's no Kb values. In fact, I only see Ka values. And it turns out that there's a reason for that. We don't need to be given the Kb values because of the conjugate relationship. so because of the conjugate relationship, this holds true. Ka times Kb for conjugate pairs is equal to Kw. That is, if the acid's strong, then its conjugate base must be weak. If the base is strong, its conjugate acid must be weak. And so there's this seesaw relationship between Ka and Kb based on this conjugate pair. And so we never really need a Kb value as long as we have the Ka value for its conjugate base. And so the Kb1 here is going to equal Kw divided by the Ka for what acid? Well, we have to figure out what is the conjugate acid of phosphate. If this is the base, what is its conjugate acid? Well, it's here, HPO4 2 minus. And so this will be the Ka for HPO4 2 minus. Kw we have memorized, 1.0 times 10 to the minus 14. We have memorized that for 25 degrees C, but what happens if the temperature changes? We don't have the numbers memorized, but we should know what happens. You know, let's say the temperature increased above 25 degrees C. Would Kw increase, decrease, or stay the same? It will increase. Why? Well, should it increase? Why does it increase? More kinetic energy. Right. At higher temperatures, you have a higher average kinetic energy, which shifts. Can you visualize the curve? You know, what was that curve called? Distribution curve, or Maxwell-Boltzmann, or thermal distribution. And so it's going to shift that whole curve to the right, more kinetic energy, which means more collisions and more reaction, resulting in higher concentrations of ions. Well, going here, Ka for HPO4 2 minus, we can find that on the chart there. It says 2.2 times 10 to the minus 15, but that chart data is a little older than our book, and so let's use our book's data. Does somebody have the book, Andy?
Where is it in the book?
In the middle of chapter 16. Where phosphoric acid is located. It'll have the Ka value for phosphoric acid, dihydrogen phosphate, monohydrogen phosphate. I think it's 2.4 or 4.2 times 10 to the minus 13.
And 4.2 times 10 to the minus 13.
Okay, 4.2 times 10 to the minus 13. Which gives me a Kv value of 0.02. Punch this out. Close to 1/4.
Oh,
238. Let's go 26, please. One extra. So 0.0238, that's our Kb. So we had to figure that out. And then we'll see. The sodium ions stop at 0.300, but the phosphate we carried from step I. And we have our 0.100 molar initial. And we know that this is a base. It's a weak base. Weak bases do what? Partially hydrolyzed with water. So we can figure out the amount of hydrolysis by just resetting this to 0, and then we'll have it change. I don't know what X is, but I know it's partial hydrolysis. And then E plus X plus X. So at equilibrium, I'm going to have 0.100 minus x, x molar, x molar. Is that the AC system? See how hot tomorrow is going to be in Japan. This AC is just crazy. So let's figure out what x is. X is going to equal, well, you know, KB is equal to the HPO4 2 minus concentration times the hydroxide concentration in equilibrium divided by the phosphate concentration. So the monohydrogen phosphate is X, hydroxide is X, phosphate is 0.100 minus X. Okay, we should just go ahead and try the simplifying assumption. It doesn't take much time. If you do the simplifying assumption, we're going to ignore the change here, the X, and then calculate it. So it'd be 0.0238 times 0.1, take the square root of that, and that gives us an X of
0.0487.
0.0487. 0.0487. You should be able to calculate the percentage in your head. There's 100 parts minus 48.7. So there's a 48.7% change. Is it valid? No. So the essay fails. If the essay fails, then what do we need to do? The quadratic. Let's go ahead and solve the quadratic. Let's get a new quadratic form. So this is going to be x squared minus plus. So plus 0.0238x and then minus 0.00238 is equal to 0. And x is equal to Does somebody have it already?
Point 038. I mean, yeah, 383.
Yeah. 0.0383. So it wasn't a 48% change, it was more like a 38% change. So the simplifying assumption was way off. And so this is 0.100 minus 0.0383. So we have a 38.3% change, and that leaves us with 0.0617. So 61.7 of our phosphate stays as is, and 38.3% was converted into monohydrogen phosphate and hydroxide. This is 0.0383 molar, 0.0383 molar. Okay, what do we do next? We double check it. And so let's go ahead and double check this, make sure that K is correct. So that'd be 0.0383 squared divided by 0.0617.
.02377.
0.02377. What do you think? Does it look good? Yeah? Should be 0.0238. We got 0.02377. Is that good? Yeah, that's good. And so it looks like everything's good so far, except something. I changed the phosphate. Phosphate changed. Is that going to upset my step I? Did it just screw up my step I because now the phosphate is less? Does it? No, not at all. Because step I, we know that K is very large, so it's not going to change anything. We have a K that's very large. Nothing's going to perturb it. All right, are we done here? Are we done here? I don't know, because this is multiple equilibria, so we got a lot going on here. So what should I do next? I have some choices here. I know exactly what to do next, right? Do you? Maybe, maybe not, you know, because sometimes you set up a routine and you'll know what to do. Sometimes you go off on the wrong path, which is very easy to do, because it's like this. I have the jungle path analogy. Since most of you haven't heard, have you heard the jungle path analogy? Except for Jasmine. Jasmine, you should know the jungle path analogy. Maybe I'll say it again. I haven't had most of you for Chem 1A. So it's just different than the morning class. The morning class is all former Chem 1A students. So they're already tired of hearing the jungle path analogy. But the jungle path analogy goes like this. You know, you watch somebody who's solved these for 20 or 30 years. You know, obviously they're going to do it and make it look easy, right? Nothing to it. But that's because, you know, they've been walking the jungle for 20 or 30 years, so they know every single path in the jungle, right? But here you are, you're lost in the jungle. Which path do you take? Do you know which path to take? No, and so sometimes you're going to take the wrong path, right? And go in the wrong direction because you don't know. And so this is the problem. When you follow somebody along, and this happens, you follow some, oh, that makes sense, that looks easy. And then it comes time for the exam, and then all of a sudden you're thinking, why didn't they go this way, or why didn't they go that way, you know? And you end up going in the wrong path. And this is why it's so important to repeat the problems, but repeat the problems as if you're starting fresh, like you've never done it before. Right? And so here we have some choices, because we're dealing with multiple equilibria. We got to figure out which equilibrium should we do next. Should we do KW next? Because we generate some hydroxide, and we know hydroxide and hydronium are going to have some kind of equilibrium in KW. Or do we deal with this? No. If we deal with this one, then HPO42 minus is what we call an amphoteric species, because it occurs on both sides of the acid-base chart. And so with HPO42 minus, should we do the Ka or the Kb for this next? Well, maybe we should see which one is bigger, right? And so what is the Ka for HPO42 minus? Somebody just looked it up. It's 4.2 times 10 to the minus 13. What is Kb for HPO42 minus? Well, Kb, is it 0.0238? Was that the Kb? Is the conjugate relationship? Is that it? No, this was the Kb for what? This is the Kb for phosphate. Do I have phosphate here? No. And so the Kb for monohydrogen phosphate is different. The Kb for monohydrogen phosphate is equal to the Kw divided by the Ka for its conjugate acid. What is the conjugate acid of monohydrogen phosphate? H2PO4 minus. Does everybody see that? Okay. And so I need Kw, which is 1.0 times 10 to the minus 14, divided by Ka for H2PO4 minus, which I'm not going to use that value. I'm going to use the value in our book. The value in our book is 6. 6.3 times 10 to the negative 8. Which gives me a KB value of 1.58 times 10 to the negative 7. Okay, the reason it's amphoteric is because monohydrogen phosphate can collide with water in two ways. If it collides with water, it can either lose its proton or it can gain its proton. In a Ka, what happens to monohydrogen phosphate? It loses. So the lone pair on oxygen here, which is an sp3 lone pair gets pushed over here into this S and knocks these electrons out, and we end up with PO4 3 minus and H3O plus. Right, this is the Ka collision. The Kb collision happens when this lone pair on the oxygen gets pushed into these, knocks the proton off, and we end up with H2PO4 minus and hydroxide. These collisions happen all the time. Can you stop these collisions from happening? No. And how do you know which way it breaks? You know? There's going to be collisions. So both of these collisions are happening. This is why it's amphoteric. Both the Ka and the Kb are happening. Which one do you think is more favorable, the Ka collision or the Kb collision? How can you tell which one is more favorable, the Ka collision or the Kb collision? Or are they equally as probable? I'll tell you, for water, they're equally probable. For this, though, the Kb collision is more favorable based on the magnitude of the K value. This is 10 to the minus 13. This is 10 to the minus 7, which tells me that this one is much more favorable of a collision than this one. But if this one's more favorable, then we should do Kb here, right? And then maybe Ka later, because we got to compensate for the two ways that it can collide. And so we'll do Kb for this next. That sounds right. Let's try that. So what I'm going to do is I'm going to carry this down to step 2, right? Because step 2 is going to involve monohydrogen phosphate. And in step 2, I'm doing the Kb collision, which produces hydroxide, versus the Ka collision, which produces hydronium. So if I do the Kb collision, I have hydroxide there. And so the hydroxide also is going to go to step 2. How about the phosphate? Does this phosphate drop down to step 2? Not yet. So let me erase this over here. Continue. Step 2. Step 2. Usually with the stepwise, we want to do them in order. You know, we start off with the biggest K and then work smaller. And so step 2 here is going to be this. HPO4 2 minus collides with the water molecule to produce H2PO4 minus and a hydroxide. This is called Kb for monohydrogen phosphate, which is also called Kb2 for phosphate. Kb1 is where phosphate picked up one hydrogen. Kb2 for phosphate is where phosphate picks up two hydrogens. And in this case, it'll pick up two hydrogens here. Now, initial monohydrogen phosphate, we have 0.0383. Dihydrogen phosphate, there's none, but we have hydroxide present at 0.0383 molar here. And so we have those two from step 1. So this comes down from the previous step, this comes down from the previous step, and this is going to be generated in step 2. And so here, this is going to be minus X molar. It's going to go to the side of the 0. Here. Plus X molar, plus X molar. So at equilibrium, we got 0.0383 minus X, X molar, and 0.0383 plus X molar. So we calculated the Kb2 value for phosphate, or Kb for monohydrogen phosphate. It came out 1.58 times 10 minus 7. So this is 1.58 times 10 to the minus 7. We need to solve for X. So Kb here is going to equal the dihydrogen phosphate concentration at equilibrium times the hydroxide ion concentration divided by the monohydrogen phosphate concentration at equilibrium. And so this is going to equal X times 0.0383 plus X divided by 0.0383 minus X. Should we try the simplifying assumption here? Yeah, let's try. And so the X drops out. If we apply the SA, then this is equal to 0.0383 divided by 0.0383 is 1. And so this is just equal to X. So X equals 1.58 times 10 minus 7. What is the percent change here? It would be the change, which is X divided by the initial 0.0383 times 100. Less than 5%? What is it? It should be way less, because this is 10 to the minus 7, this is like 10 to the minus 2. It's going to be very small. Times 10 to the negative. Let me just check something really quick. So I got so I get the 1.58 times 10 to the minus 7, 1.58 times 10 to the minus 7 divided by 0.0383 times 100. I get 4.12 times 10 to the minus 4%. 4.12 times 10 to the minus 4% means that no problem. Simplifying assumption works great. Why does the simplifying assumption work so great? Can somebody explain that to me? Why does the simplifying assumption work so great? It failed in step 1, but it works great in step 2 because the percent change is so small. And so based on this minuscule percent change, 10 to the minus 4%, I'm saying it works great. And so why are we getting such a minuscule change?
When you're solving for the change, the percent change,
Yeah.
you have to multiply by the 0.0383 and divide it by the same 0.0383.
No, percent change is the change divided by the initial times 100%. And so the change is X. X equals 1.58 times 10 to the minus 7. 1.58 times 10 to the minus 7. That's because if X drops out here and here, then it's 0.0383 divided by 0.0383, which is 1. And this drops out. X is just equal to K. You see X is equal to K. And so here's my K, that's the X. The initial is 0.0383. Times 100, which gave me 4.12 times 10 minus 4%, which means it's way, way lower than 5%, which means it should work great. It should work great. That is, if we did the quadratic versus the simplifying assumption, we get the same value of X. Do the quadratic to prove it to yourself. And so my question is, why is it working so great in this particular case? You know, it worked great here. Why didn't it work great in the last one? Somebody tell me why it didn't work so great in the last one, but it's working great in this one. We're trying to look for patterns.
Is it because the KB is so small that?
Yeah, one, the KB is small. Compare the two KBs. KB in the last problem, 0.028. KB in this problem, 1.58, but times 10 to the minus 7. KB is way smaller. And so the change should be way smaller. Right? But the change is only part of it. What's the other half? The initial. What was the initial in the last problem? 0.1, 100. What's the initial in this problem? 0.038. And so the initial is smaller here. If the initial is smaller, then the percent change is bigger. Right? But it isn't in this particular case because there's one huge difference. Remember that predator and prey thing? Can you apply it to this? Or do you have some analogy that you guys use for it instead? What was the difference? There's another major difference between the previous step and this step. What is it? In the previous step, we had
Initial concentration of hydroxide at 0.
0 and 0. You know, 0 and 0, right? In this step, we have 0.038. And so we have a significant amount of product already, which means the whole predator and prey business comes into play. We don't expect much change because the hydroxide is going to limit how much H2PO4 minus. That's one way of thinking about it. Another way that I used to use in thinking about it is the Le Chatelier's inhibition of the forward reaction. The more product we have, the less forward reaction we're going to have, right? And so as the concentration of the product builds up higher and higher, it tends to favor the reverse reaction. Well, we can't go reverse here because we got 0. There's only one way to go here, and that's forward, but we can't go forward too far because we got too much hydroxide there to begin with. And so that's going to limit how much of this is formed. And so the other reason I expect this to work great is because we got lots of product there already. We don't expect much forward reaction to occur. And so the simplifying assumption would be expected to work well in this type of setup. Okay, going on here, let's go ahead and calculate the concentrations here. So this is 0.0383 minus X. So let's get X into decimal form. That's going to be 6 zeros. 1, 2, 3, 4, 5, 6 zeros, 1, 5, 8. So let's add some zeros here so we can do this subtraction. So this 10 from 8 is 2. 9 from 5 is 4, 9 from 1 is 8, and this will be 9, 9, this will be 2, 8, 3, 0. So we went from 0.038 to 0.038299842. Was the change very significant? No. Here the change is significant, because now we're going to have 1.58 times 10 to the minus 7 molar. And over here, we're going to have 0.0383 plus 0. And we need 6 zeros. And a 158. Let's add some more zeros here. And this is going to be 0.038300158. Did that concentration change much? No. Do you see, would you agree that this is a negligible addition of hydroxide? Since this is a negligible addition of hydroxide, will that perturb step 1 or not? No, step 1 should still be good, at equilibrium. I.e., if you double check it with this concentration now, you're going to get the same K essentially. I'm not going to change it. And so we're good here with step 2. Okay, so far, how late do we go till?
12:40.
12:40? Well, I just had a lot of questions in the morning on chapter 15, so that's why I'm going to be far ahead of the morning class now, but that's all right. Because always doing let's see something. So what should I do about step 3? You know, that's one. This was the KB collision, right? For monohydrogen phosphate. Should we now look at the Ka collision for monohydrogen phosphate? Monohydrogen phosphate's amphoteric, and so it can collide with water in 2 ways. It can collide with water to produce hydroxide, and it can collide with water to produce hydronium. When monohydrogen phosphate collides with water to produce hydronium, transfer a proton this way, we're going to form phosphate and hydronium. So should we do this? This is going to be the Ka for monohydrogen phosphate next. Yes or no? No? I see a lot of head shaking. No. Why am I going to ignore this collision? Does a collision happen? Yes. Why would you ignore this collision?
Wouldn't it be like insignificant change?
Yeah, it's not going to be that significant because Ka is very small. So you're going to say, I'm going to ignore this because Ka is small. True or false? You're going to ignore this because Ka is false. I mean, small. Ka is small.
Okay.
So you'd write that down. We're going to ignore this because Ka is small. Yes? No.
No?
No. Otherwise, we'd ignore Kw, right? We'd ignore Kw because Kw is even smaller. So that doesn't. It's not going to work. So should we do it?
Now we do.
No.
Oh, what?
No, we aren't going to do this because, you know, this is redundant. It doesn't look like it's redundant, but it is redundant. Why is it redundant? It's redundant because this describes the equilibrium between these 2 species. Didn't we just solve that? Yeah, except we solved it. It was the equilibrium between phosphate and monohydrogen phosphate in terms of, this is redundant. We just solved this equilibrium in terms of hydroxide. But do you know hydroxide and hydronium are connected? In other words, we solved this in terms of pOH. But we know that if the pOH goes up, the pH must go down, or if the pH goes up, the pOH must go down. There's a seesaw relationship there. And so this is redundant. We just solved this equilibrium in terms of hydroxide POH. This is the exact same equilibrium except in terms of hydronium. Hydronium and hydroxide are related by Kw. In other words, the pH plus the POH has to equal 14 pKw. And so, you know, if we did this, we're going to get the exact same concentrations, you know, that we got before, or not, you know, pretty much the exact same concentration. The only difference is, rather than a hydroxide ion concentration, we have a hydronium ion concentration. And so when we're dealing with amphoterics, normally you have to consider both collisions, right? The Ka collision and the Kb collision in dealing with multiple equilibria. But this is going to happen frequently. Therefore, we come up with this general rule. For base solutions, only consider KBs and KWs. You ignore all the KAs because those would be redundant. All KAs redundant. And so for bases, we only look for hydroxide contributors. We do not care about hydronium contributors. There's only going to be one hydronium contributor, and that's going to be Kw at the end. And so even though we're dealing with amphoterics and you expect hydronium, well, we're going to compensate for that hydronium at the end with Kw. And so for bases, only hydroxide contributors. For acids, only Kas. Even though there could be a bunch of Kbs around, we ignore them. For acids, only hydronium ion contributors. Because the KBs, the hydroxide ion contributors, would be redundant. We already solved those. And so, even though, you know, something like phosphate, when we look at all the equilibria, we're generating a whole bunch of amphoteric species, and these amphoteric species can go either way, but this collision's already been taken care of. This one here. And so this is not step 3. Here, what is step 3? Step 3 is, we call KB3 for phosphate. And so far phosphate's picked up 2 protons. KB1 was the first proton, KB2 is the second proton. Now it's going to pick up the third and final proton, which we're going to call KB3. This is going to produce hydroxide. So this is KB for dihydrogen phosphate. Kb for dihydrogen phosphate is also known as Kb3 for phosphate. Phosphate being a tribasic base. And so what is that Kb value equal to? That Kb value is going to equal this. It's Kw divided by the Ka for, what's the conjugate acid of dihydrogen phosphate? H3PO4. Now, dihydrogen phosphate is amphoteric. So dihydrogen phosphate itself has a Kb for dihydrogen phosphate and a Ka for dihydrogen phosphate. Somebody looked up the Ka value earlier. It was what, 6.8 times 10 to the minus 8 or something like that? 6.3 times 10 to the minus 8. Are we going to do anything with? No, we're not going to do anything with that other than calculate our KBs. And so this is going to be 1.0 times 10 to the negative 14 divided by the Ka for phosphoric acid, which is 7.1 times 10 to the negative 3, which gives us a Kb of
1.4 times 10 to the negative
Times 10 to the negative
12.
12. 1.40?
Yeah.
1.40 times 10 to the negative 12. So I'm going to carry some stuff down from step 2 down to step 3. I'm going to carry two things, the hydroxide and the dihydrogen phosphate. And so how much was it at the end? It was 0.060 zeros, right? 158. And the hydroxide? Was 0.038300158. Is that right?
Yes.
And then initial phosphoric acid would be 0. Change here is going to be minus x, plus x, plus x. So at equilibrium, we're going to have 0.000000158. Was that right for dihydrogen phosphate?
1.58 times 10 to the negative 7.
7, yeah.
Okay, molar plus minus x molar. This is going to be x molar. This is 0.038300158 plus x. I don't have to carry that many digits, but I'm just carrying it just to keep track. We plug it in here to see how it comes out. That's going to be x times 0.038300158 plus x divided by 0.000000158 minus x. How about here? You know, you look at that KB is quite small, 10 to the minus 12, so you're thinking that the simplifying assumption should work pretty good here, right? And it should work pretty good. And look at how much hydroxide we got there. Huge amount of hydroxide, right? Which is product. You're going to inhibit the forward reaction. And so the simplifying assumption is looking very good right now, except there's one problem. Take a look at the two initials. You know, if you look at the top initial, it's pretty big. But if you look at the bottom initial here, it's pretty small. And since I have such a small initial amount here, I'm worried. Because even if I lose a tiny bit, even if I lose a tiny bit from a tiny bit is a lot, right? And so I'm pretty good with the simplifying assumption working up here, but I'm worried it might not work down here, but you know what? I'll just try it anyway. And so let's just go ahead and try it and see. If I drop the x here, then it's going to be 1.4 times 10 minus 12 times 1.58 times 10 minus 7 divided by 0.038300158. And what does x come out to?
5.77 times 10 to the negative 18.
5.77 times 10 to the negative 18. Which, when I calculate the percent change, should I calculate the percent change based on the bigger initial, or should I calculate the percent change based on the smaller initial? The smaller initial. So let's go ahead and calculate the percent change. The percent change would be the change, which is x, divided by the initial, times 100.
3.65 times 10 to the negative 9.
Which means no problem. No problem. And so even I was worried about this because of the minuscule amount, it still worked. Okay. And so the amount of H2CO4 minus I lose is extremely small, so wait, am I out of time? Shoot, I didn't finish this. Oh, we got 5 minutes? Okay, I'll finish it. 158, okay, minus, now how many zeros do I need? I need 17 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and then a 1, 4, 8, or 1, 4 zeros. That is a insignificant change, wouldn't you say? You can punch it out in your calculator. Tell me what your calculator gives you as the answer to this. I'm just curious. I'm just curious if your calculator is going to round it off or if it's going to give it to you.
$1.579986 times 10 to the negative 7.
So you got 0.6 zeros, 157.
9986.
9986. Did I get the decimal places wrong?
Yeah, you did 17 zeros instead of 11 zeros, because it's since the negative 12.
Oh, okay, I misread it, sorry. 11 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Wait, subtract the 5.77.
Oh. Yeah, oops, sorry. It should be 17 zeros, sorry. It should be 17 zeros. 5, 7, 7. 17 zeros. What does your calculator give you?
1.58 times 10 to the negative 7.
Is that right? Did your calculator just give you the right answer? No, your calculator gave you the wrong answer, so redo it in your calculator. It cannot be, because that's subtracting nothing. Right? If you redo it in your calculator, what do you get? Huh?
I got no change.
You got no change, but there was a change. Your calculator is not giving you the right answer. Right? The calculator is giving you the wrong answer. Why is the calculator giving you the wrong answer? It's too many digits. Your calculator is only capable of storing how many decimal places? Or is that how many digits? 8 digits probably, or 10 digits at the most. This goes beyond it, and therefore you're going to have what we call round off error. To avoid the round off error, then we better not use our calculator. We better do this by hand, right? And so I'm going to do this by hand. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 5, 7, 7. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then 0, 0, 0. And so this is going to be 3, 9 from 7 is 2, 9 from 5 is 4, 9, 9, 9, 9, 9, 9, 9, 9, 7, 5, 1, 0, 0, 0, 0, 0, 0, 0. This is the right answer, right? And so do you see your calculator failed you? This is it?
Mine gave me that.
Oh, yours gave you that? You have a Oh, okay. Well, maybe the calculator is getting better. But, you know, this happens more often than you might think. And therefore, sometimes you have to do what we call reset. You know. reset. But anyway, this is it. Was it a significant change? No, it wasn't. How about here? Yes. 5.77. We need to double check this though. I'm still minus 18. I still didn't finish this. And was this a significant change? No. No. And then double check it. And then after step 3, we go to step 4, if necessary. We'll look at step 4. But anyway, did step 3 add a significant quantity of hydroxide to perturb step 2? No. So stepwise is working good. So we don't have to do simultaneous. All right, I'm going to stop here.